the nilpotent cone in rank 3. So take it away, Anna.
Okay, thanks so much to the organizer and everyone that's made possible for my talk to be today. So I know a speaker was concerned, many thanks for that. So today I'm going to talk about an old acquaintance of the theory of Higgs bundles and more generally of vector bundles. So I'll be focusing on the global nilpotent cone, but also mentioning very centrally the wobbly locus. So this wobbly locus has been in the scene for 40 years since the work of Lomon, but attention has gone back to it since the program by Janagi and Pantev on the proof of geometric Langlands from abelianization. So maybe let me start by the beginning. I may not be very historically accurate at some points. It's for the sake of compactness and clarity, so you will forgive me. So maybe I should turn off my video because you won't see me anyway. So, okay. As I said, this goes back to the work of Lomon in 81, who studied the global nilpotent cone. And also Drinfeld, who, well, he's cited in this paper of Lomon's. So to explain what the objects are, let me fix some notation. So I will be working with the moduli space of rank n degree D Higgs bundles. So this parameterizes pairs. So the closed points are pairs given by a rank n degree D vector bundle and a Higgs field, which is a section of the holomorphic section endomorphisms tensor with a canonical bundle. And of course, this is all over a curve of genus at least 2, smooth, projective, and so on. I will also be mentioning the moduli space of bundles. So the notation is similar. I will just use an n. So this is the moduli space of vector bundles of invariants given by n and d. Okay, so how do I add a page to whiteboard? Sorry, up, there you go. Okay, right, so there is the Hitchin map that to a Higgs bundle assigns the characteristic polynomial of the Higgs field. So this is determined by a bunch of sections of line bundles. Let's call this B for the Hitchin base. So this is the Hitchin map. So it assigns to a pair E5 the characteristic polynomial of the Higgs field. So a priori, this is just a identity. This is just a formal object, but the coefficients are well-defined sections taking values in the successive powers of the canonical bundle. Okay, so it turns out that Higgs field, given a Higgs bundle, a Higgs field is nilpotent. This is a theorem of constants. If and only if the image under the Hitchin map is 0. So the global nilpotent cone will be for us just the pre-image of on the 0 section. So Lomon studied it in the more general setup of stacks, but we will be thinking about the moduli space. Okay, so this is just pairs of vector bundles and Higgs fields such that the Higgs field is nilpotent. And they are semi-stable, of course. Okay, so if phi being nilpotent induces the iterated kernel filtration on E, so we have filtration of length L. Oops. So Tom is on the way in my whiteboard. So let me put this E, there you go. Okay, so this is the kernel, EI will be the kernel of phi I plus 1. Okay, so we get a filtration of length L, where L is the order of nilpotency of the Higgs field. And Lemon defined some invariants linked to this filtration, which he called the type. So associated to the filtration, we have the graded pieces, say Fi equals EI mod EI minus 1. And the degree of phi Fi, say Di. And the rank of Fi will be called Ni. So we have the pair Dn, right? Which, or rather Nd, I think I'll use, but anyways. So these are the degrees and the ranks of iterated piece of graded pieces. Okay, so these are two sequences of length L. So for example, Lomon proved that the type stratifies the nilpotent cone by types. So there's a stratification by types. And say, moreover, if one takes the closure of a stratum, say CND closure of a stratum, then these are Lagrangian inside the nilpotent cone. All right, so we now know that the components of the nilpotent cone are in fact the reducible components of the nilpotent cone are classified by these types. This follows from the work of many people: Ginsburg, Lomon, Faltings, Gotham, Bradlow, Garcia Prada, Heinloth, and Bozek as well. And to give an example of one of these components, let's just examine the most simple ones is the trivial filtration, right? So we just have the rank and the degree. So of course, these are just bundles with nilpotent Higgs field 0. So in fact, this is the underlying reduced scheme is just a copy of the moduli space of bundles. Right, so to semi-stable bundle, one assigns the Higgs bundle with 0 nilpotent Higgs field. Okay, so an important feature we will be using is the C-star action. Let me also mention that this is important in other ways because it's also a fixed point component of the C-star action. So the C-star action on the moduli space. So here we have the nilpotent cone. So as we saw, we have one of the irreducible components, which is just the moduli space of Higgs bundles. And there will be others. This is irreducible, so they will intersect at some sets. But more importantly, any Higgs bundle, and this is why the nilpotent cone is so crucial in the study of of the modular space of Higgs bundles, any Higgs bundle can be brought to the nilpotent cone by letting C star act on it. So this action is just given by multiplication on the Higgs field. And properness of the Hitchin map, so this would be the moduli space, this would be the Hitchin base. So by properness of the Hitchin map, one always finds a limit at 0. So these will hit different fixed point sets. So there's the moduli space of bundles, as I just mentioned, but there will be others. So this is the fixed component 0, F1, and so on. And also, one can do this game inside the nilpotent cone, right? So starting with some Higgs bundle inside the nilpotent cone, one can flow it to 0. In fact, it can also be flown to infinity. And one of our characters today is precisely the flow of Higgs bundles down to the moduli space of bundles. So Le Monde, and this is historically very inaccurate, observed that flowing down the flowing down bundles in the nilpotent cone hits a non-generic locus of the moduli space of bundle. And this is precisely the wobbly locus. Which consists precisely of Higgs fields, Higgs bundles, sorry, with, so E semi-stable and phi nilpotent. Sorry, this is wrong. It lives inside the modular space. So these are semi-stable bundles such that there exists a non-zero nilpotent Higgs field. Okay. So in fact, Le Monde was interested more in the complement, which are the famous very stable bundles. So these define a dense open subset inside the moduli space, so they capture a lot of its geometry. But W, it's interesting in its own right. So this this is an announcement by Drinfeld, who claimed that W is of pure codimension 1. Okay, so this it defines the divisor, so a geometrically interesting object. Okay, so far, the only available proof is due to Paolo and Pauli in rank 2. And I'll be talking today about joint work with Pauli about the rank 3 case. Okay, so our goal for this project is mostly not just to study the rank 3 case, but provide an inductive method to construct the nilpotent cone in rank from lower rank, in rank n from rank M, and also to check proof codimensionality of the wobbly locus. Okay, are there any questions so far before I get into the
Yes, I have a question. So,
Yeah.
can you turn to the previous page when you take the limit going to
Here?
0, and then you say that the limit lies in the wobbly locus? Do you assume that E is already semi-stable?
Yeah, you need to assume that it is already semi-stable. That's
Yeah, okay.
right.
Okay, thanks.
Okay. Okay. Any more questions? Okay. So in rank 3, there are 3 possibilities to consider. So given E phi, so always phi is nilpotent, there are 3 possibilities. Either phi is 0, and we're in the moduli space, we're happy, we know about it. It could be that phi squared equals 0, and then we would be talking about components of the nilpotent cone of type 2, 1. They are classified by an invariant delta that I will explain in a minute. And finally, it could happen that we have a filtration of order 3, of length 3. So nilpotency order 3. And this is the most interesting case where we see the both the inductivity or the recurrence in place, and new ideas come into the picture. Okay, so these would be components of type. So these are classified by 2 invariants, and the rank of the graded pieces would be 1 for all graded pieces. So these will be the components we will find. So I will define also the wobbly components. So wobbly delta, say delta bar, and then n bar to be the intersection with the moduli space of bundles. Okay. So not all of these will be divisors. These we will see already in type 2-1. But anyways, they are subsets of the irreducible components of the nilpotent cone. Okay, so since the length 2 filtration is very similar to rank 2 and the latter is clearer, let me just remind the work of Alan Pauli. Okay, so the setup is the following. We have E phi. Now it's a rank 2 Higgs bundle. Say, let me call it D, not to change notation, but this is a different moduli space, so nilpotent. Okay, so we have that E has just a filtration. Now the graded pieces are the same as the kernel of the Higgs field and the co-kernel of the Higgs field, right? So we have an extension of this form. And we observe that an nilpotent Higgs field is totally determined by the following. So one can map a point in E to F and then to F0, okay, by some section. So C is a section of H0. Of this line bundle. All right, so what we are saying is that we're taking extensions of F1 by F0, but we have an extra condition on these 2 line bundles, namely that F1, F0K has a section. So it's equal to O of some divisor. So the invariant I will mention, so the invariant we will consider is the degree of this divisor, which is determined, of course, by the degrees of F0 and F1. Okay, so extensions, so more precisely, we want to consider Higgs bundle extensions of this form. So we are extending the 0 Higgs bundle of rank 1 by, so this one, by another 0 Higgs bundle of rank 1. And these, by work of Thaddeus, are classified by a hypercohomology of a complex. So this complex is just a two-step complex, which is very simple. So there's just, one is just mapping a shift to another one through 0. So this is Thaddeus. He did this while studying deformations of parabolic, but it works in this setup too. Okay, fine. So the statement by Pal and Pauli is the following. So we have a scheme which is just given by the following. One has, we have started by D0, D1. We're going to consider certain extensions of these guys. But in fact, we need for an extra condition, okay, which is for a section to exist once we twist them suitably. So we will consider the following. Inside the Jacobian of degree delta times the Jacobian of degree 0, there's the symmetric product of the curve delta times. So if delta is at most G minus 1, otherwise we will just take the Jacobian because all line bundles have sections of degree delta. And we take the fiber product of these two. Right, so what they proved is that there exists a rational vector bundle. So it's not defined everywhere, but over a generic, over an open, a dense open subset, whose fiber over a given point. So we have a divisor and a line bundle are the extensions. So sorry, it's the hypercohomology of the given complex. So the complex depends on D and F0. And moreover, if one projectivizes this bundle, there is a rational map to the moduli space of Higgs bundles intersected with the nilpotent cone. And the closure of the image is an irreducible component. Whenever the invariant is at least 0 and smaller than 2G minus 2. Okay, and all components are like this. Okay, so this gives the components of the nilpotent cone regarding the wobbly locus, what happens in this case? Well, it's not hard to see. And this works for any rank. Now, what we want to see, so we have the moduli space of bundles and we have some component here flowing down to it. Okay, so something one can consider is using Lagrangianicity of the components of the nilpotent cone is to consider the orthogonal space to the any given Higgs field flowing down to a given E. And this defines a hyperplane inside the tangent bundle to the moduli space. So in this way, one can prove very easily that the corresponding wobbly set, say, to that component is, yes, I should write it like that, is a divisor if and only if there exists a unique have someone's face in my, I can't, if I write here, I cannot, right? So let me do like this, if and only if there exists a unique line of Higgs fields. Intersecting the corresponding component. Okay. And using this, they can see that W11 delta is a divisor is at most G minus 1. They also prove actually something interesting is that for delta greater than G minus 1, for delta greater than G, the wobbly component is contained in a wobbly divisor. So D max is the maximum of all the deltas, which are congruent to the degree mod 2. This is a requirement I didn't mention before, but this is always the case. Okay, so this is important in proving pure codimensionality, right? Because otherwise we would have some other irreducible components that have higher codimension. Also, something interesting here is that there's half of the irreducible components of the nilpotent cone in rank 2 collapse to higher codimension sets, and the other half give divisors. Okay, so a very similar phenomenon. Oh, I have, okay, I have to start a new keyboard, a new whiteboard, it seems. Maybe I have to stop sharing and restart.
Can you please save the document?
Oh no, let me see. I didn't. Wait, because it's my whiteboard, isn't it?
Yes.
No worries.
Okay, I'll look for it later. Hopefully I have it. Sorry about that. Okay. All right. Okay, so from this, it's rather straightforward to grasp what happens in rank 3 when the Higgs field squares to 0. So again, we will be looking at length 2 filtrations. So now the difference is that this has rank 2 and this is rank 1. So a priori one could, I mean, a priori E0 could be unstable, but in fact, this won't be generically the case. So we define the invariant of a given Higgs field to be, so the degree of F1 E0K, which is D0 minus 2, D1 plus 4D minus 4. And so let me write here a table. So let's compare the rank 2 case and the rank 3 length 2 filtration case. So what we had here is that, so we had an extension of a line bundle by another one, also in terms of Higgs fields, Higgs bundles. So what we wanted, one of the conditions was for F1 dual F0K to have a section. In rank 3, we have the same. In fact, this is F0. We're extending a rank 1 Higgs bundle with 0 Higgs field by a rank 2 Higgs bundle with 0 Higgs field. And this condition becomes for F1 dual E0K to belong to the Brill-Netter locus of rank 2 degree delta. So this is the Brill-Netter locus, which is defined as bundles in the moduli space of rank 2 degree delta bundles, such that there exists at least a section of E. And then we have the condition that ruled semi-stability. So this says the bundle is wobbly. This says it is semi-stable, and likewise, we find that for delta at most 4G minus 4, delta always congruent to degree mod 3. Here we have delta congruent to degree mod 2. Then the components will be non-empty. Okay, so now the theorem in this case, everything works as before. Let's we have that, I mean, this is a and this is already known, but this would give a new way to check it. The component is non-empty if and only if we have the invariant in the range I just explained. Also, we have that the wobbly locus is a divisor if and only if delta is at most 2G minus 2. And this is again the phenomenon of having at most a line of Higgs bundles. This is just saying that the point F1 E0K is generic inside the Brill-Netter locus. And finally, we prove as well that if the wobbly locus is not a divisor, then it is contained inside another wobbly locus. So this is the maximum of 0 and delta. Such that delta is congruent to D mod 3. Okay, so as a corollary, the wobbly locus of type 2-1 is of pure codimension 1. And I should say if delta is greater than 2g minus 2, sorry. Okay, and moreover, similarly to the former case, one can explicitly describe the components in terms of a given rational vector bundle over the following scheme. So one has, so let's write things properly. So we started with a modulus with a rank 2 bundle of degree D0. This is the kernel, and the co-kernel has degree D1. And then we map them to the moduli space of rank 2 degree delta times rank 1 degree D1 bundles. So we just take the Brill-Netter locus times the Jacobian and take the Cartesian product. So over this Cartesian product, we have a rational vector bundle with fiber over, say, E0 F1 equals the hypercohomology of the complex given by what we, so we would be considering. So we have the following complex. It sends a section of E0 F1 dual to 0. I mean, this is just a 0 complex. And then the component of type delta to 1 is birational to the projectivization of this bundle. Okay. Are there any questions? Okay, so in a similar fashion, we're pretty confident, we haven't checked out all the details, but these would generalize to any extension, any filtrations of length 2 of arbitrary rank. So this would be the next step for us to check. And now let me talk about the most interesting case. So phi squared would not be 0 and phi cubed is 0 now. Okay, so in this case, one has a filtration of length 3. And the remark is that the kernel of phi is itself wobbly. That is, it admits a Higgs field, a non-trivial Higgs field induced by phi. So, in other words, one can construct an element in a component of the nilpotent cone of rank 2 by taking the kernel and the induced Higgs field. It could be unstable, but the same happens if one takes the co-kernel of phi. A Higgs field is induced on it from phi just because phi of E0 goes to 0 by definition, so one can just take the quotient Higgs field, and this is likewise an element of some irreducible I mean, some component of the nilpotent cone, possibly stacking. But not both can be unstable. So at least one of them is stable if we are starting from a semi-stable component. Okay, so this is what sets the induction in place. So just as before, we're going to be considering pairs then. So we will be considering pairs of nilpotent Higgs bundles of rank 2 with different invariants. There is an extra condition. If we want for them to be induced by a rank 3 Higgs bundle, we need to impose the co-kernel of this one is the kernel of that one, right? So in other words, we have, I mean, this will be a subspace of the direct product. And by what I explained in the former section, these fibers over the Jacobian of D0 times a symmetric power of some delta 1 of the curve. So we just take the pairs such that D1 here and here is the same. So we eliminate one G degrees of freedom. Okay. Right, so we want to consider Higgs bundles of this form, extensions of F00 by E1 phi 1, or extensions of Q0 phi 0 by F00. Okay, sorry, this is F2. Okay, in fact, we should have both if we are doing the right thing. So one of them will be semi-stable. Suppose it is this one. This is seemingly not symmetric, but we will see that it turns symmetric in a minute. Okay, so we will be taking extensions. So these live in the hypercohomology of this complex Q0, F0. Right, which fits in fact into an exact sequence of this form. Okay, so as you see, here is the extension of the Higgs field. Here is the extension of the bundle, okay? Okay, so I was talking in my former slide about pairs of nilpotent Higgs fields. So this would be E1 and this would be Q0 with their respective Higgs field. This is too much information, but we will cancel this out in a minute. So can I move this? Let me write it in here. Firstly, because not all extensions will be of type 111, there will be extensions of type 21 appearing, and we want to eliminate those. Otherwise, we will get too many dimensions. And in fact, this is captured by a subscheme of this. sorry. These pairs of components of the nilpotent cone. So these would be given by the following. So now recall from the former section, points in here are given by a divisor, a lane bundle, an extension, which will be the E1, and some section. And here we have the same divisor, lane bundle, Q0, and a section R, okay? So the scheme Z will be given by elements of this, by pairs of this form satisfying D1 cut product Q0 plus E1 cut product D2 equals 0. Okay, I'm not sure how much longer do I have left just to try to explain what the idea behind this is, or go a bit further and give a...
You've got 15 minutes.
Oh, 15 minutes, great. Then I have plenty of time, good. Okay, so, okay, let's see why this condition comes into the picture. And notice, by the way, that this solves the symmetry problem, because here we have the Higgs field on E, here we have Q0, here we have E1, and here we have the Higgs field on Q0, and they appear in the same, in the same right. None has more importance than the other. Okay, so why is this the right condition? Fine, so we have, let me express, we're considering the following complex, Q0, F0 to Q0, F0, K. And in here, since recall it, so Q0 is the co-kernel of the Higgs field. And so it's an extension of the second graded piece by the third graded piece. So this can be completed to two exact sequences. 0, 0. Okay, so let's call this this complex D, this complex is C, and this complex is E. So this induces a long exact sequence in hypercohomology. So we would have H1 of C, which is what we're interested in. This gives us Higgs bundle extensions. And this maps to H1 of E, which in turn maps to H2 of D. And this is split. So, no, sorry, this is not split. This is just H1 of F0, F2K. This is the one that's split. So this would be H0 of F0, F1K. H1 of F0, F1. Okay, so notice now that this map, one can define maps alpha 1, say, and alpha 2. So whatever extension this co-cycle is parameterized in, we want for it to come from a Higgs bundle of type 111. And so we want for alpha 1 of C to be non-zero, and alpha 2 of C should be E1. This is the extension type of E1, right? So in other words, this map, which is given by cup Q0, cup product Q0 here, and plus D1, D2 here, should should have a non-trivial kernel. Otherwise, we will have that the image of C under alpha 1 plus alpha 2 will be 0. And this means that whatever extension we take is not of type 1, 1, 1. So what the condition is we want for ker QQ0 plus D2, whatever, is not empty. So it's different to 0. Okay, and in particular, these are precisely, so we want for our pairs to satisfy that, say we started with extensions of Q0 by F0, then we want to consider E1s and D1s in the kernel of the map I just described. Okay, and precisely the kernel of this map will give the admissible E1 and D1s for the extension to come from a type 111 bundle. Okay, so to finish, let me maybe write things in a bit more compact way. Okay, so we have the following proposition. So if we have the appropriate range of delta i's, then there exists a vector bundle over Z delta 1, delta 2, 1, 1, 1, parametrizing. So this is a rational vector bundle, parametrizing type 1, 1, 1 extensions. Of say F0, say extensions as Higgs bundles of F0, F2, 0 by 0, by 0. On the other, yeah, no, the other way around. Okay. Such that, so this is a subbundle. So we have a map into C delta 2. So over this scheme, we can consider a rational vector bundle which parameterizes just extensions. In this case, this would be Q0, and this would give us F0. And V is a subbundle of the pullback. In other words, the conditions on Z can be made compatible to the final linear subspace of extensions of the Higgs bundle. Okay. Last thing I can say is that the dimension of P of V is the right one. It's 9G minus 8. We cannot claim it's an irreducible component because we haven't been able to prove that there's always a rational map. So there we need to check rationality, existence of stable extensions, and this we haven't done so far. But I mean, we're pretty confident this is going to work. So the hypothesis, say, to finish, is that the components are non-empty if and only if they're in, I mean, the invariants are in the range I just gave. And they will be birational to this PV. And also for wobbly guys, we are persuaded that they are divisors if and only if delta 1 plus delta 2 is at minus 3G minus 3. So there's a nice picture of ranges. So let me draw it here. So this would be delta 1, this would be delta 2. So this is the line to delta 1 plus delta 2 equals 6. Line to delta 2 plus delta 1 equals 16 minus 6. This is the point 2G minus 2G minus 2. Okay, so in this range, both E1 and Q0 are generically stable, semi-stable. In this range, E1 is unstable and Q1 is stable. And in this range, Q0 is unstable and E1 is semi-stable. And the shaded area, say, gives the range for which the wobbly locus is a divisor. Okay, so I think I'll stop here. Thanks for your attention and sorry for the technical issues.
No problem with that. Thank you very much. Okay, are there any questions for Anna?
Maybe quite a general question. So for any Higgs bundle, for any bundle E, and let's say it admits, can it admit more than one filtration defined by kernel of nilpotent Higgs field?
Yeah, it can. So for example, this is what happens when you have these wobbly loci that collapse to lower components of the nilpotent foam that collapse to lower dimensional components. So what happens is that there are Higgs fields coming from different components that flow down to the same point. So it has to be discarded, yes.
Let's see. So in general, for example, in the vector space of, so the subspace of nilpotent Higgs field in the space of all Higgs field for a fixed bundle can be very complicated.
Say that again, sorry.
So for a fixed bundle E, and I consider the space of all Higgs field on it, then the subspace of nilpotent Higgs field on it can have complicated geometry.
I mean, it could. I mean, the problem, if you assume that it is stable, no. But if you assume that it is, for example, semi-stable, there will be automorphisms coming into play. So as equivalence classes of Higgs bundles and bundles don't match. So for example, there are very stable bundles. There are some semi-stable bundles which admit non-zero nilpotent Higgs fields, but which only yield a point in the moduli space of bundles in the Higgs moduli space, because there's equivalence class of that bundle with whatever nilpotent Higgs field you take is the point given by the bundle with 0. So yeah, I mean, unless it is stable, things can happen. There will be automorphisms, so that makes it complicated.
But you're saying that for stable bundles, because they are only trivial automorphisms, then it can be complicated for that reason, right?
No, so I don't know what you mean by complicated, but for stable Higgs bundles, you know what for stable bundles, you know what Higgs bundles are. It's just a vector space. It's the space of sections of the endomorphism bundle tensor with the canonical bundle.
Yes.
And we know things about that, yeah.
And because all the automorphisms are just scaling, and so I mean, there can be multiple components of the subspace of nilpotent Higgs field, and they don't get reduced.
Sorry, can you say that again? They don't. What doesn't get reduced? So you have
they don't collapse into anything when we use the automorphism to represent.
Well, no, but they can. There can be different filtrations even if it's stable. So what you're maybe what you're asking is whether the intersection with the nilpotent cone can be complicated. Yes, we know it's a cone, but it need not be a vector space. So in that sense, yeah, there can be awkward things happening.
I'm asking just for I'm not getting into it, even the moduli space yet, but just about. Well, let's say for fixed wobbly, then I'm asking whether the space of nilpotent Higgs field, which is just a subspace of the finite dimensional subspace of all Higgs field on it, can that subspace have complicated geometry?
Yeah, it could. Yeah.
Because we can have multiple filtrations.
Yeah, exactly. I mean, there's even, if you take Higgs bundles over a point already there, you have different components of the nilpotent variety. So yes, it's not trivial. Yeah.
Yes, and okay, thanks.
No problem.
Are there any other questions? Can I just ask, so did Drinfeld state this thing about pure codimension 1? I mean, did he prove it, and what was his his proof?
I have no idea. So this is a big question mark in the whole issue, because only Lomond quotes a letter to, I think, Deline. I don't remember. I think it's Deline, where he claims that this is a pure codimension 1, but the proof is not there. So he maybe knows how to prove it, but it's not available in any case. Right,
and there wasn't some kind of conceptual idea why he thought this was true? Or...
Not in Lomond's paper, no, and the letter I haven't found, so.
One other little question. I mean, many of us have found that studying meromorphic Higgs bundles is sometimes easier than studying the real things. Did anyone study these questions for like meromorphic Higgs bundles on P1 or something, where maybe they reduced to some kind of linear algebra?
Yes. So Donaghy and Pantev have in their paper about Hecke eigenships. So they describe the wobbly divisors fully. So they get what's expected. But I don't think anyone has generally done that. For meromorphic guys. So their motivation was to check whether their method works for, to prove geometric Langlands, if they could find the Hecke eigenships, and they could in this case. But it was not about the geometry of the nilpotent cone in particular.
And how about point counts? Do people know the number of points of this nilpotent cone? Probably they do, actually.
What do you mean, the number of?
Like if I did this over FQ, like I'm meaning some sort of enumerative invariance of this thing. So like if you did it over FQ and then counted the points, or I mean, are those?
Yeah, I guess Hausel is the person to ask. I don't know about this, but
it's just the way you're doing this kind of inductive structure looks perfectly set for kind of counting the number of points of it somehow by sending this argument. But,
okay, interesting. I hadn't that in mind, but
any other questions? Okay, if not, let's thank Anna very much again. Thank you.
Thank you.
And then I think the floor is going to be left open for questions and discussions about anything we like. I think this is going to be pretty informal. So anyone who wants to go home, feel very free. But